We will solve irodov problem 187. In this problem, a disk is striking a wall and it is making perfectly elastic collision. The angle at which it is striking is alpha. The collision is perfectly elastic. Now let us find out what will be the velocity and what will be the angle. By intuition we can say it will be alpha, but we should see how it comes. Now let us resolve the incoming velocity, which is v, into two components. One is v sine alpha and in this direction will be v cos alpha. There is no force along y-axis, but force is there along x-axis. Since there is no force along y-axis, the velocity component in that direction where the no force acts on the body, that is the disk, will remain same. So v sine alpha here and v sine alpha here. But as far as the perpendicular velocity is concerned, there is an impulse which is acting on it, and since both kinetic energy and momentum are conserved, velocity of separation is velocity of approach, and in all such collisions which is elastic, as far as the head-on velocity is concerned, if the incoming is v cos alpha here, outgoing will be v cos alpha, just the direction gets reversed. So if we write vector, v final will be minus vector v initial as far as perpendicular velocity is concerned. So the velocity, return velocity, is in this direction, v cos alpha. Since if you take now these triangles, the vectors, if you look at, this was the incoming and this was the resultant v, because v sine alpha here, v cos alpha here. Now you have v sine alpha here and again v cos alpha here, so the resultant will make the same angle here, alpha. So that is why I said the angle will remain the same. Now we have to find out the points along which the angular momentum is conserved. Now the points along which the angular momentum is conserved, let us try to find out along which point it can be. Along point O, of course, there is no momentum at all, angular momentum at all, because it is passing through it. Now let us take some point O dash here, draw a perpendicular. If this length is OO dash, this will be OO dash sine alpha. And what will be the angular momentum about O dash? Angular momentum will be mvoo dash sine alpha. And what will be the direction? If you look at the top, the rotation is like this. This is the direction of the rotation, but if you look at the vector will point into the paper, because angular momentum is to be found by this thumb rule, right hand thumb rule. If this is the rotation, this is the direction. If we see here, the rotation is like this, the thumb is pointing downwards. So the direction is downwards. I am showing by cross as far as the vector is concerned. Now when it is coming back, use the same point, draw the perpendicular. Since this angle is same, this is again OO dash sine alpha, and again we see the rotation remains the same, so vector is still pointing like this downwards. So angular momentum final, angular m final will again be mvoo dash sine alpha, so there is no change. So whatever points we take along the perpendicular, the angular momentum is conserved. So this is the part 1 of the answer. As far as part 2 is concerned, we have to find angular momentum about a point O1 or O dash, whatever you may call it. Oh, this is just a notation, it doesn't make any difference. What happens to the angular momentum about O1. So draw a straight path, draw the perpendicular. This angle is alpha, so this angle will also be alpha. This is L, this will be L cos alpha. So initial angular momentum will be mvl cos alpha, and if we look again, it is from the top, we can see The rotation is like this, so vector is pointing again downwards. Now what about the momentum when it is going back from this point? Draw the perpendicular, and what is this distance is same and mv is same, so it is mvl cos alpha again, but now here you have to see the direction of rotation is just opposite, so the momentum vector points upwards. So if we take this as the reference, then this will be minus, or if we take this as the reference, if we take final as the reference, then this will be the minus. So change in momentum will be mvl cos alpha minus mvl cos alpha is equal to twice mvl cos alpha. L is the length here. We can write small m. Don't get confused with the vector L. So that is the change in angular momentum.